Our next speaker is Su-Chen from National Taiwan University, talking about a learning-based framework to handle multi-round, multi-party influence maximization on social networks.
Hello, everyone. Thanks for coming. My name is Shou-Chen. I'm a PhD student from National Taiwan University. Today, I will share my work, a learning-based framework to handle multi-round, multi-party influence maximization on social network. I started this work under the advisory of Professor Shou-De and Professor Ming-Syan. We are all from National Taiwan University. In a decade, influence maximization is a eye-catching task in social network. We want to select a small set of key persons to influence the most number of persons through the information propagation. We know the viral marketing is a classical application for influence maximization. A company tends to select a small set of customers to distribute their trial product with the hope that this customer can share their praise to a larger propagation with the most of effect. In this paper, we target on competitive influence maximization, which is a natural extension of influence maximization. In real world, multiple concepts from different parties are propagated in a social network. Besides, propagation may interfere with each other, as a single node can only be active by only one type of concept. We call this problem as a competitive influence maximization or multi-party influence maximization, which assumes multi-concepts to be propagated and compete with each other in a social network. This is an example of competitive scenario. Different internet service provider parties provide their own cell phone plan to customers. However, each person can submit only one plan. In this competitive scenario, influence maximization for single party may fail due to the existence of competitor. If the T-Mobile gives the free product to the red one, and expect the red one can share their good review to his friend or his friends of friends to attract them to join T-Mobile. However, if there exists a blue one using AT&T, and the blue one also influences his friends, in this situation, the T-Mobile information cannot propagate as the T-Mobile company expect. So the influence maximization for single party has to be modified for this scenario. In our work, we consider multi-round competitive influence maximization. Since the marketing is a long-term process, we model it in multiple rounds. We use the example to illustrate the multi-round competitive influence maximization problem. The red and blue two parties want to expand their influence in the social network. Given the weighted graph and the diffusion network, they separate choose C nodes and obtain the new influence nodes through the information propagation. This is round one. The red choose one node and the blue choose one, and then perform propagate. In the end of the first round, the red party gets 5 nodes and the blue party gets 4. So in the next round, the red party choose a node again, so does the blue party. They propagate to get a new network occupation status. This choosing and propagation process will continue to reach the predefined run. In the example, the predefined run is 3. In the example, the red and blue party obtain 11 and 12 nodes in the end, respectively. In the example, the relative inverse node of red party is -1, and the blue party is 1. In the multi-round competitive inference maximization problem, the goal of each party is to choose one node in each round to maximize his relative inference in the end. So next, we subscribe the limitation of previous work in inference maximization. Most previous work solve inference maximization using model-driven method. This method applies certain heuristics to choose node. Given a predefined inference diffusion model, such as a linear threshold model or independent cascade model. One concern for such method is that they cannot adapt the network topology. This figure shows the competitive inference maximization in real P2P and Facebook network. The degree and weight are two strategies. They against the same opponents. In P2P network, we can see degree is more effective than weight, but the opposite is observed in Facebook network. From this observation, we can know that the best strategy varies for different networks. So the typical model-driven approach cannot handle the general network. So we have to design a flexible and general method to adapt not only the opponent's strategy but also the network environment, such as underlying network topology and the diffusion network. To design such a general framework, we design a learning-based framework in which a policy is determined based on the inference. Based on the inference outcome, that is data. The critical issue of data-driven approach is the sparsity of training data. It is hard to obtain real record of two parties competing with each other. A possible workaround is to generate opponent strategy for training. However, random generated opponent strategy can be biased. So to improve the feasibility of building a data-driven model, here we proposed a strategy to exploit the inference outcome for training an optimal policy. To be more precise, our framework performs data generation and model learning at the same time. Here we define the policy is to output an existing inference strategy given the observation occupation status. In model learning, the policy is refined by the inference outcome feedbacks. In data generation, the inference outcomes are generated through the simulation by applying the current policy. Through this interactive process, we can overcome the sparsity of the training data and train a good model at the same time. With the above idea, we propose STROM, strategy-oriented reinforcement learning-based inference maximization framework. STROM is a meta-learning framework. It learns a policy to select existing inference maximization strategy. Instead of selecting signal directly, he also utilized a reinforcement learning to maximize the long-term inference. Reinforcement learning changes optimal policy through interacting with the network environment and the opponents. Through the interacting process, the reinforcement learning gets a new inference outcome, that is the inference gain in a certain occupation status using a certain strategy. To maximize the long-term inference, STROM considers both the inference gain at the current run and the inference in the future. He used Q-table to record the expected long-term inference, avoid being myopic on short-term gain. When the STROM obtained a new inference outcome, he updated Q-table using this question. He used learning rate alpha to update Q-table, and the last term is the expected inference from this new inference outcome. The red part is the blue part is the inference gain at the current run. The red is the expected inference from the next run to the future. So we specifically consider these three opponent scenarios we can simulate to generate training data. The first scenario assumes the opponents used a known strategy for every run, which our model can simulate to generate training data by applying this strategy and learn an optimal policy to win. The second scenario assumes the opponent strategy is unknown but available for training, in which our model can gradually learn a policy through the competing with it. Although the scenario 1 and 2 are different, we can use the similar way to update Q-table. In these two scenarios, we construct one agent. We construct one agent for this system, and the opponent selection is treated as a part of environment feedback. We propose Q-learning to update the Q-table following the concept of Q-learning. The third scenario is which assumes opponent's strategy is unknown and not available for training. This is the most challenging one. So we introduce how to handle this scenario in the following. In the third scenario, when the opponent's strategy is unknown and not available for training, we assume these parties are rational. In other words, all of them want to maximize his own inference. We construct multi-agent for multi-party. Each agent determines his strategy by maximizing his inference based on his own Q-table. Their training data is the inference outcome, which are generated by multi-party competing with each other. Following the above simulated system, we propose two approaches to simulating rational parties: STROM QQ and STROM MM. Double Q and double M means that we apply the same way to update the Q-table. The STROM QQ is adaptive from Q-learning. He updates his expected inference by considering one side, that is his own strategy. the second one, STROM QQ, is adaptive from min-max-q learning. He updates his expected inference by consider both sides. That, in other words, he maximizes his inference and also minimizes the opponent's inference by consider his strategy and opponent's strategy at the same time. Here is an experiment. We use the Facebook P2P and 3 citation network as a data set. If the data is a weighted graph, we use the original weight we use his original weight information. Others are assigned a random weight. If we use the degree weight blocking and the subgreedy as our candidate strategy. The optimal policy in STROM is to choose one of them to apply in each round. We also compare STROM with these 4 fixed strategies. For example, the fixed strategy degree is that we always apply degree in each round. In addition, we compare STROM with 2 meta strategies, which also use the fusion of these 4 candidate strategies with a certain policy that are random voting. In the experiment 1, when the opponent strategy is given, STROM Q can significantly outperform the opponents. Each row represents a relative inverse of STROM Q trained with the certain strategy, and each row represents the opponents. We can see that in each column which STROM Q against the same opponent strategy. The STROM Q can get the best performance when training and testing against the same strategy. In the second experiment, we want to verify if STROM Q works well when the opponent strategy is unknown but available for training. We can see the result no matter which strategy the unknown opponents used. Can STROM Q gradually learn how to beat the opponents, achieving high score after training? In the third experiment, when the opponent strategy is unknown and not available for training, our solution can yield a better result than other solutions. The left figure shows the average performance of the competing algorithm against 6 strategies over 5 networks. The blue bars are the fixed strategy. The orange are the meta strategy. The red bar are our proposed STROM QQ and MM, which are outperform others. The red figure shows the average score of competing algorithms against all possible combination of candidate strategy. If we have 10 rounds, the number of combination is 4 power 10 is a very large number. In this figure, we can see our proposed STROM QQ is the best one. Here is the quick conclusion. We propose a meta-learning framework using reinforcement learning for competitive inference maximization that generalized a meta strategy to combine existing strategy. And also, we propose a data-driven framework to exploit the inference outcome for learning an optimal policy. In the future work, we want to extend our work to support partial observed network and adapt the other network in one model. Thank you. Any question?
Unfortunately, we don't have time for questions, so that will have to be offline. If you're interested, please contact the speaker after the session.